You know, for over a century, one humble metal has been our invisible guardian, protecting us from some of the most powerful forces in the universe. But its story, well, it's a lot more complex and a whole lot heavier than you might think.
We've all been there, right? You're at the dentist, and for a quick 2-second X-ray, they drape this ridiculously heavy apron over you. It feels like you're wearing a suit of armor. And you're probably thinking, is all this really necessary? Well, it turns out that weight is the entire point.
See, the reason that thing is so heavy isn't just because it's thick. The secret is actually hidden inside the atoms of one particular metal, lead. It's got these atomic superpowers that make it the hands-down champion of blocking radiation.
So what is it about this one element that makes it so special? Well, it really all boils down to two fundamental superpowers.
Lead's effectiveness really comes down to being both atomically massive and physically dense. Think of it like this. It creates an incredibly target-rich environment for radiation to hit, and then it packs a ridiculous number of those targets into a very, very small space.
So first up, its atomic number is 82. This means every single atom of lead has a massive nucleus that's surrounded by this dense cloud of 82 electrons. For an incoming energy packet, like an X-ray, trying to fly through that is like trying to navigate a dense asteroid field. A collision is pretty much guaranteed.
And second, it is just incredibly dense. At over 11 grams per cubic centimeter, lead packs way more of those supersized asteroid field atoms into a given area than other materials. And this is exactly why a very thin sheet of lead is so much more effective than a great big thick wall of concrete.
Okay, so we've got these two superpowers, a huge atom, and tons of them packed tightly together. But how do they actually work to stop dangerous radiation? Turns out it's not just one trick, it's more like a three-pronged attack.
Lead uses 3 different physical mechanisms to stop radiation: the photoelectric effect, Compton scattering, and pair production. Which strategy it uses depends entirely on the energy of the radiation it's up against.
At lower energies, think the X-rays at the dentist office, the photoelectric effect is the dominant move. An incoming photon hits an inner electron and is just completely absorbed. Poof, gone. And in the process, it knocks that electron right out of the atom. Now here's the wild part. The chance of this happening is proportional to the atomic number to the power of 3 or even 4. That high atomic number of 82 makes lead exponentially better at this than pretty much anything else.
At medium energies, the strategy shifts to Compton scattering. This time, the photon isn't absorbed. Instead, it collides with an outer electron like a billiard ball, loses some energy, and just careens off in a different direction. This interaction depends on how many electrons are packed into a space, which is where lead's extreme physical density becomes the MVP. More atoms packed together simply means more electrons to block the path.
And then for the really high energy photons, there's something that sounds like science fiction: pair production. As a photon zips past lead's massive nucleus, the intense electric field from its 82 protons can cause the photon to spontaneously convert its energy into matter, creating an electron and a positron, basically out of thin air. And the probability of this happening? It increases with the square of the atomic number. Once again, lead's atomic might gives it a huge advantage.
So this is the key takeaway right here. Lead's high atomic number makes it a master of the photoelectric effect and pair production. Meanwhile, its sheer physical density makes it a champion of Compton scattering. It's a triple threat. But here's where the story takes a turn. Because for all its power against energy waves like X-rays and gamma rays, lead is not the perfect shield. It has some surprising and sometimes even dangerous blind spots.
That's right, using lead to shield against the wrong kind of radiation doesn't just fail to protect you, it can actually create a whole new radiation hazard.
The key distinction is this. Lead is a superhero against photons, which are packets of electromagnetic energy like X-rays. But it's surprisingly weak against actual particle radiation, like fast-moving electrons and neutrons.
So take beta particles, for instance, which are just high-speed electrons. If you put lead in their path, its powerful nucleus slams on the brakes so hard that the electrons shed their energy as secondary X-rays. This is called bremsstrahlung, which literally means breaking radiation. So to shield beta particles safely, you first have to use a low-density material like plastic to slow them down gently, and then you use lead to stop that breaking radiation.
This quote really nails lead's problem with neutrons. See,
Neutrons have no charge, so they ignore the electron cloud and have to hit a nucleus directly. But a tiny neutron hitting a massive lead nucleus is like a ping pong ball hitting a bowling ball. It just bounces right off, barely slowing down. To stop neutrons, you need something their own size, like the hydrogen atoms you find in water or concrete. And beyond the physics, there's some very real, very practical problems with relying so heavily on this ancient metal.
I mean, for all its protective power, let's not forget lead is also a potent neurotoxin, and its sheer weight is a major occupational hazard. Medical professionals who have to wear those lead aprons for hours every day often end up suffering from chronic back and joint pain.
All of this has spurred a big search for alternatives. You've got tungsten, which is even denser than lead, but it's expensive and brittle. Bismuth is non-toxic and it has a similar atomic number, but it also costs more. And then there's concrete, which is cheap and structural, but you need a massive amount of it to do the same job.
And this chart right here really drives the point home. To stop half the gamma rays from a standard source, you need less than a centimeter of lead. To get that same protection from concrete, you need a slab nearly 5 centimeters thick. That's almost 7 times the material. Lead is simply unparalleled in its efficiency.
So, this is the core dilemma, isn't it? And it's what's pushing researchers to innovate and look for the next generation of shielding materials.
The future, it seems, lies in advanced materials. Researchers are developing nanocomposites that embed metallic nanoparticles into lightweight polymers to boost shielding power without all the weight. They're also designing these smart, hybrid, multi-layered materials that can stop both photons and neutrons in one single package.
Which leaves us with the ultimate question. Lead set the gold standard over 100 years ago, combining near-perfect physics with low cost. The challenge for modern science is to create something that can match its incredible power, but without its very heavy price.